We're doing Unit 2 this week. Unit 2 was the bonding unit. So there's Sean. So this was the bonding unit. And this we actually did this year. So this should be reviewed from this year, but it was very beginning of the year. So it may it may have been a minute. So we'll review all through this. But otherwise, for all these weeks, everything is basically the same. Like we're doing the same thing, just with different units. So you'll see this document looks almost exactly the same as last year. This is still split into 2 big videos for these topics. And we've got a presentation review, and we'll do free response questions at the end of the week. So all of that being said, that's not what I meant to do. There we go. So quick recap from last week. People who actually, first off, did anybody actually watch those 2 College Board review videos? Anybody watch them?
They wouldn't load on my computer.
They would not load?
I kept trying to open AP Classroom or College Board, and my computer was like,
no. It said no.
Right.
Because the videos are on YouTube. Like those are just YouTube links. So the 2 videos you can just watch on YouTube. They really are quite good. So if there is anything we're going through where you're just like, don't remember that, I would go and find that information on the videos and watch them. But regardless, let's move on to Unit 2, talking about structure and bonding.
Yes.
Whee! Okay, so again, there's the 2 videos that I've got direct links to on the plan. So there are 7 objectives for this one. And we'll start with just basic types of bonding, which we went through really fast. But all bonding is based on electronegativity, which we talked about last time. That is your ability to attract a shared pair of electrons, all right? So this is talking about attraction in a bond. And who attracts the most? Which element?
Fluorine.
Yes, fluorine. Okay. So that means as you move left to right across the period, getting closer to fluorine, you have higher electronegativity. That also means as you are at the top of a column, all right, or top of a group, you have higher electronegativity. So your lowest electronegativity is where?
Francium.
Francium. Okay, so if you basically remember fluorine's the most, francium is the weakest, then you can make a general comparison of electronegativities. There is no such thing as needing to know actual electronegativity values. It is just always going to be able to kind of like make a general comparison. So closer to fluorine, more electronegative, closer to francium, less electronegative.
I forgot though, what's more important? Like if there's 2 elements that are like diagonal to each other, right next to each other, what would be the first? How would you know which one is more has more electronegativity? Like if it's
we do tend to always consider the placement in a group up or down to be more important than left or right.
Okay.
Because the difference in energy levels makes a larger difference than the small difference in number of protons.
Right.
Okay. Polarity. Polarity is how well are you sharing? So remember my whole definition of sharing was what you do with a Kit Kat, right? A Kit Kat comes with 4 pieces. You can equally share and give 2 pieces to somebody and keep 2 pieces to yourself, or you can unequally share and give 1 piece to somebody and keep 3 pieces for yourself. That is all considered to be what?
Or you can take a bite out of them while they're still connected and have them all for yourself.
Well, that's just weird.
Well, that is a
I'm
hate
sure
crime.
that would actually be sharing.
You're sharing with yourself.
No, sharing with yourself is not sharing. That's being a noble gas, Carl.
Well, I guess I'm just too noble for you guys then.
Okay, fine.
Not y'all making chemistry jokes.
You get it though. You get it. You understand.
I'm sorry if I
I
have.
wish I didn't.
I know, but you're nerds and I love you. So polar things are the unequal things and non-polar things are the equal things. Is any of that ringing a bell as familiar?
Mm-hmm.
Okay, good.
Yes.
Okay, good. Okay, so that chart right there summarizes our different types of bonds. And the electronegativity difference numbers on the right, you do not need to know that. You basically need to know the general principle on the left here, right? If there is no difference in electronegativity, you are going to have a purely nonpolar covalent bond. The more difference in electronegativity you have, the more polar you become, until your difference in electronegativity is so large that you just snatch electrons and you become an ionic bond. Okay, so it would behoove somebody to put that left part of the diagram onto your collaborative notes, because that would be helpful.
I have a question.
Yes.
So you said so somebody like in the what's it called in the collaborative notes, someone would just put this like this chart looking, or not the chart, but like the arrow part.
I would put this part here.
Okay.
The left hand with the arrow. Yeah, this arrow part. Yeah, this left part. Not the actual table.
Do they usually not like ask like, so what difference in electronegativity would you need to
because
have this
then
type
they'd
of
have
bond?
to because then they'd have to provide you with numbers, and that is not necessary.
Okay.
Besides the fact it's not an actual hard and fast rule, and different people have different definitions of where non-polar versus polar is, and when you go from polar to ionic. So yeah. Okay, so practice problems. Now, they did actually provide you a chart here, but we can still just kind of base it on your general, like, is it closer to fluorine, farther to fluorine? And we'll look. So these compounds, in order of increasing polarity, so who would be the most nonpolar and who would be the most polar, and then figure out the others. So looking at that list, you should very immediately be able to tell who is the most polar.
HF.
HF, because it's got the fluorine, right?
Mhm.
So that's your most polar. So that's going to be your first one or your last one?
First one.
No, last one.
Last
Last
one.
one.
Last one, increasing polarity. Okay, so that's your last one. So then looking at that, your first one is going to be whoever's got electronegativities that are almost the same.
SO.
Wait, so we're picking out two of these that are going to be similar?
I think SO2 and C and CCl.
CCl.
CH4.
CH4 is your least polar.
Why?
Oh, I thought you said which ones
Because
are
they're-
going next to each other.
2.55 and 2.20. So the weird thing is hydrogen being a is still a nonmetal, but it's not all the way over there. So hydrogen's electronegativity is almost exactly the same as carbon's. And that's where you can see here, carbon and hydrogen is a very nonpolar bond. So my first thing is going to be the CH4. My last thing is going to be the HF, and then figure out between the SO2 and the CCl4, the polarity there.
Is it CCl4 then SO2?
Yes, ma'am.
Ms. Baskin, when you're looking at the electronegativity values, do you like multiply if there are two things, or do you just look at?
No, you just look at the relative difference.
Mm-hmm.
Because the bond is just between the two things, right? Yeah. Okay. So, and looking at this list, who is going to be the most ionic?
The sulfur fluoride.
Wait.
I have a question.
Yes.
I don't understand what the question is asking me.
Which of those is the most ionic, right? So ionic meaning that you've got the largest difference in electronegativity.
Okay, yes.
NAF, right?
Yes, NAF. So you don't actually need the electronegativity values to figure this one out. You can literally look at your periodic table and say which two elements are farthest apart on the periodic table. The farther apart they are, the larger their electronegativity difference is. The only element you can't do that trick with is hydrogen. But if you're talking about compounds that don't have hydrogen, you can literally just say the farther apart they are on your physical periodic table, the more ionic they are because of the electronegativity trends.
So Miss Baskin,
Yes.
is polarity and like being ionic, they're the same thing? Like to be polar and to be ionic are the same?
To be polar is to be getting close to being ionic.
Okay.
Because you become ionic when you like polar, or like when you're the most.
So looking at this last question, it kind of gets to what you, Nala and Sean, were just talking about. So which kinds of bonds can be polar or non-polar?
Covalent.
Only covalent, right? Only covalent can be polar or non-polar. But once you become so polar, you actually are no longer a covalent bond, you become ionic. Does that make sense?
Yes.
Okay. All right. Okay. So this is a mildly misplaced question, except it does, because this unit and the next unit kind of go together in many ways. So this is methane down here, that's CH4. And it says, which kind of, which of the following would exist between multiple molecules of methane? So is methane, are you going to have ionic bonds between multiple molecules?
No.
No. All right, ionic bonds are only inside molecules, except they're not even inside molecules because molecules implies covalent. Are you going to have non-polar covalent bonds between molecules?
No.
No, again, not between molecules. Can you have polar covalent bonds between molecules?
No.
Nope.
No. Again, those first three things are bonds inside compounds. But between molecules, you're going to have one of the next two things. So intermolecular attractions resulting from temporary dipoles or intermolecular attractions resulting from permanent dipoles. Meaning, does this thing have polar bonds?
It's the permanent one.
No, they're not polar because C and H have like relatively the same electronegativity.
Oh.
C and H have relatively the same electronegativity. So these do not have polar bonds. So if they do not have polar bonds, which ones do you have? Temporary or permanent?
Temporary.
Temporary, right? So if you remember, LDF, London dispersion forces, which we will review next week, that's what you have between non-polar things. So this question is basically, do you understand that methane, CH4, has nothing but nonpolar bonds, and therefore it can only have LDF.
So are they nonpolar because their electronegativities are similar?
Yes, ma'am.
Yay.
Just
Yeah.
asking, wasn't it like,
Yeah,
sorry.
Taylor?
Go ahead.
Wasn't it like when I remember us doing like charts and having to fill it in, like you would give us like a word bank, and most of the time, like the intermolecular or whatever the compound like would always have like LDF. Wasn't that like the most common one or something like that?
Because everybody has LDF.
Right.
Yep.
That's
Oh,
what I was
yeah.
trying to say.
That's what we'll get to. Is everybody has LDF.
Miss Baskin.
Yes, Sean.
So you said the ionic, nonpolar, and polar covalent bonds. You said they wouldn't be between. You wouldn't consider them to be between, like inside a molecule, because that implies covalent. So would you just say like what would you say those things are between?
Okay, so covalent bonds are in a molecule.
Okay.
Because molecule implies covalent bonding.
Okay.
Right? A molecule is a distinct little unit of something. Ionic bonds, however, are not inside molecules. They're inside crystal lattices. You remember?
Latrice.
We are about to talk about some Latrice. So
yes.
Come on, Google. There we go.
Ms. Baskin, the sentence that you just told Sean, you said ionic bonds are not in molecules because they're in the trees?
Because they're in crystal lattices, yes.
Thank you.
Molecules are distinct units, and ionic bonds do not make distinct units. They make crystals. Okay, so this next one is basically, this is a whole thing on interpreting that diagram. We talked about this diagram, I promise. Does it at all look familiar?
Yep.
Yes, because yes.
Oh yeah.
Yes. Did I understand it when you first went over it? No.
That's okay. So before I start putting up words, basically, if I have two atoms far apart, how much attraction do they have?
A lot.
Not a whole lot, right? They're far apart. As you put them closer and closer, what happens to their amount of attraction?
It increases.
It increases. And as the attraction increases, you get to basically a happy point down here where they have attracted, they are very stable, they are happy, and that's at the low point of the diagram. Okay? Because when you make a bond here, that's all the way down here at the bottom, you release this much energy out into the world because of your happiness. So as you continue to try and shove those atoms closer and closer and closer, however, the energy goes way, way up because they do not like that.
They're repelling.
Because you get them so close that they start repelling. So what this graph tells us is it illustrates the energy between two atoms based on their distance. So the lowest part shows how much energy would be needed to now pull these guys apart, right? They are super happy down here. And to reverse this state, to pull them apart, would require 436 kilojoules per mole of energy. It also tells you how far apart those two nuclei are in this bond. So they are 74 pm or picometers apart. That's their bond length. This bond length clearly is going to depend on what atoms you are talking about. And that will also affect how much energy there is, because different atoms with their different numbers of protons and electrons are going to have different amounts of attraction. So this number will change based on the number of protons and electrons, and this distance number will change based on the size of the individual atoms. So remember, if you squish them too close together, they're going to be super, super happy or super unhappy. Okay. we remember single, double, and triple bonds, yes?
Yes.
Okay, and remember 2, 4, 6, 1 line, 2 line, 3 lines?
Yes.
Okay. They don't normally use the term bond order anymore. Bond order just means the number of lines you draw in the bond. Right? But the strength of a bond, who is the strongest bond between single, double, and triple?
Triple.
Triple, right? It's real easy to think about, like, okay, this is like a stack of 3 boards that I'm trying to karate chop through. That is super hard to do. It takes lots and lots of energy to break 3 boards when I'm doing karate. So a triple bond is the strongest. A single bond breaking 1 board, you know, you can teach a 6-year-old to do that. So that's a weaker bond. But then the bond length, who is the longest bond?
One.
Single, double, or triple?
One.
Single.
The single, the one, right? Because as you put more electrons in between things to make a double or a triple bond, that means there's more attraction in that bond and they're actually pulling closer and closer and closer. So a triple bond is part of the reason it's very strong is because there's so much stuff in the bond and it's all so close together. Okay, so it gets pulled closer and closer together. All right.
Dang, Miss Baskin, can you go back? I just want to screenshot it.
Yep.
Thank you. I got it. Thank you, Miss Baskin.
Okay. All right, Coulomb's law, like, good Lord, we know Coulomb's law.
Miss Baskin,
Yes.
real quick, was there a particular type of name for the graph from 2 slides ago?
No. It's just
Okay.
a potential energy bond diagram thing. And there's going to be several more here in examples.
Okay.
Yes. Okay. So, see, here's another one. Okay. So if my 2 atoms here had a larger atomic radius, what would be different? How would the shape of this graph be different if these yellow orange balls were bigger?
They have a greater separation distance.
Okay, so greater separation distance is what, X or Y?
That's X.
X. So would this graph be shifted to the left or to the right?
To the right.
To the right. Yes.
I don't understand that.
Yeah, you lost me.
Okay. So my x-axis is my distance. If these 2 circles were bigger, the distance between them when they got happy would be bigger, yes? So bigger is further out here to the right.
Wait, but is that because they need to get close? They have to get, wouldn't they need to get closer?
No, they can't get any closer.
Oh, because they can't get any closer.
Right, yeah. I mean, you got bigger, fatter atoms. They're still only so close that they can get. And because each of them is bigger and fatter, well, they're still just kind of farther apart. It's a difference between 2 skinny people hugging and their arms wrap all the way around each other and 2 really fat people hugging and their arms just kind of like barely wrap around to their shoulder blades.
Don't attack my family.
Oh, wow.
No, but I'm just playing. But so if I wanted to think about this in terms of like Lashot, like in terms of like, okay, well, what was I about to say? Hold on. So like if I take away like some of the closeness or like if I take away some of the closeness from one side and it shifts, anyway, never mind.
Yeah, I was about to say, I'm not sure that really pertains here. So, but basically you shift this thing to the right.
But see,
I have a question, or like to maybe expound upon Taylor's thought, like you decrease like their like the closeness of them on one, like on the right, and so it'll shift to the right if you want to think about it like that.
That's what I was trying Does that
But I
make
mean,
that
it's
make
not
sense?
actually how it works, but like that's a way to think about it.
Right, but that's just like
Okay. I mean, I can maybe see that.
not saying like the shot like actually applies here, but like the thought of like if you take something away from one side of something, it's gonna shift, balance out thing type of stuff.
Just drawing, y'all.
Okay.
Thank you, Chris.
Prepare yourselves.
Thank you, Sean.
No problem. No problem.
So if this is the diagram, right?
Mm-hmm.
Okay. So if we have bigger circles now. My artistry here. All right. Bigger circles. That means as close as they can get, what it's saying is that this whole thing would kind of shift like that. Because these big circles are only so close they can get.
Mhm.
And right on top of each other is still bad, right? But like the distance here from here to here is clearly bigger than the distance from here to here. So that's why this shifts this way. And if these two things are bigger, there's actually less attraction between them as well, which is why this goes up here, okay? Because that means that there's less attraction because bigger atoms.
Miss Baskin?
Yes.
So the fat ones would be like if francium and some other big atom made a bond. And then the small ones are like, I don't know, what's small?
So if you had,
Hydrogen
so say, imagine the green ones are like chlorines, right?
Oh.
Two chlorines coming together, and the blue ones are like two iodines coming together, right? There's a significant difference between the size of iodine and chlorine. So, and since iodine is so much bigger, they're not coming as close to each other, which means they also don't have as much attraction. So it's both easier to break the iodine bond apart. It doesn't have as much energy, and it is physically larger. That's all this graph is showing. Okay. Back to the thing. Cool. Okay. So again, right, because they have put these graphs on in the past, so just to make sure that we're all fine on being able to read them. So this is talking about hydrogen and hydrogen here. Note that the bond energy is down here. This thing, that weird little A, that is a distance unit. It's called an angstrom. Don't worry about that. But the ideal bond length here, you just have to be able to recognize that that is bond length is the thing on the x-axis. All right, that is your x-axis, is bond length. Your y-axis is bond energy. That's literally all you're gonna have to remember, because anything else is just reading a graph, and you're pretty good at being able to read a graph. Yeah. You remember, this is we're about to head into talking about lattice here, lattice energy. So do you remember what factors go into how strong of an attraction ions have?
Isn't this electronegativity?
Eyes.
Ooh. We are full ions here.
Is it the charge?
Well, is it what is it?
The
like,
charge, and what is the other thing?
Bonds?
Close they get?
How
Close
many
they
bonds?
get, and how close they get is determined by their
bond length.
size. Okay. So looking at this, these charges of 2 down here would definitely be much harder to separate than these charges of 1, because Coulomb's law says we take into account both the charge and the distance. So these have more charge, right? 2 and 2 is bigger than 1 and 1. But the reason why it's this one and not this one is because beryllium and oxygen are physically smaller than calcium and selenium, and therefore they can get their charges closer to each other. Is that all sounding vaguely familiar?
Not familiar, but
No, not at
good.
all, but I'm learning.
This is all just application of Coulomb's law. Charge and distance, charge and distance. You want a small distance and a high charge to have large attraction.
Sick.
So you see what you
So-
just said, because that made sense.
Okay. So Coulomb's law is just talking about charge and distance. So we want a high amount of charge and a small distance, because that will give us the most attraction.
Miss Baskin, this face, I cannot.
What? Sorry. I forget you
But
can see my face when I'm looking at the screen.
so to connect it back to the diagrams, the beryllium and oxygen, they will be further to the left
Yes.
than the calcium and selenium.
Yes.
Okay.
Okay. And then you have to remember that more attraction means that you have a stronger bond, right? If things are super attracted to each other, they are really, really bonded. And therefore, it takes a lot to unbond them. Unbonding includes things like breaking them apart. It includes, anything to unbond would be a lot of energy. All right, Google is tired. Come on. There we go. My clicks are off here. So which of the following is going to have the greatest bond length? Greatest bond length, does that mean shortest or does that mean longest? Longest. So the longest there, how do I know with all of those things which one is the longest?
About who has like single bonds and not double and not triple, like who has the
Correct.
single.
So out of that list, who likes to make double bonds? You remember?
Oxygen.
In
Oxygen.
Calcium?
oh,
Oxygen likes
oxygen.
Calcium.
Yeah, girl, calcium ain't on this list. We're talking about NH2, and O2.
Oh, sorry.
And nitrogen likes to make 3 bonds.
Yes, it does. All right. So this is gonna kind of become what they expect to be automatic information, right? Nitrogen making triple bonds, oxygen making double bonds, and those halogens, of which chlorine is for the most part, typically only making single bonds. So chlorine is your single bond, oxygen is your double bond, nitrogen is your triple bond. So the greatest bond length is the chlorine because it's the single, but the greatest strength is going to be the nitrogen, which is the triple, okay? All right. Okay, now let's talk about lattice. All right, we remember these? Our lattice structures?
Yes.
Our crystals?
Yes, sir. Yes, sir.
Yes. Okay. So, ionic bonds, right? They have these alternating ion structures. Very organized, right? That's why we call them crystals. And since every negative is surrounded by positives and every positive is surrounded by negatives, it's not a single positive and a single negative. This is a super, super strong bond because of the super, super amount of attraction between the cations and the anions. These guys like to conduct electricity, but only in 2 different instances. They will conduct electricity when they are dissolved in water, right? Salts and water conduct electricity. But they will also conduct electricity when they are melted, when they are liquid, not when they are solids, And we don't really think of ionic things as being gases. But when they are melted or molten, they will conduct electricity, which is a little weird. And because of their strong attraction, they have incredibly high melting and boiling points, right? So this is how you can remember if you put sugar, which is a molecule covalently bonded. If you put sugar in a pan, you can melt it on the stove. But if you put salt in a pan, you are not going to be able to melt it on a stove. You will damage your pot before you start melting the salt, which is kind of funny. Okay, so why do we think ionic compounds only conduct electricity when they are melted or dissolved and not when they're solid?
There's more
Because,
wiggle room
go ahead.
for electricity to get through.
How does the
Like the
electricity
structures change. So
Because it's like the organization. Because like, because they're so organized in the crystal lattice, like the electrons can't pass through.
Correct.
Like the electrons of electricity can't pass through, but when they're like separated or melted, the electrons can pass through.
You have to remember that conducting electricity is basically like passing charge off from one thing to the next. And if they're locked in a crystal, they can't do any passing. But if they're molten or if they're dissolved, they can still pass through and move the electrons along. So it is absolutely the difference between imagining a locked in crystal versus kind of a smashy, loosey-goosey arrangement of ions in the melted or dissolved state. All right, how can you explain the difference between those two lattice energies?
Calcium has a higher charge.
Yes. Remember, anything talking about bond energy has to do with Coulomb's law. So it's either the distance or the charge. So looking at these two things, would there be much of any difference in the distance between these?
No.
Mm-mm.
No, they both have bromine, so that's the same. And if you look at the periodic table, potassium and calcium are literally right next to each other, which means they are almost exactly the same size. So it can't be distance. So it must be charge. Because the answer is always distance or charge. So here it must be the charge. And you know that calcium has a larger amount of charge. Done. So here they would probably be looking for an answer that does specifically identify that they have about the same size and identifying that the charge is greater in calcium. So it is best practice when you're talking about anything having to do with Coulomb's law to mention both size and distance. Okay. How would you even approach this question?
Did you try to structure it?
Charges.
You would deal with the charges. So if you have 3 valence electrons, what's its charge?
3.
Plus 3. And if you have 6 valence electrons?
It's 0, 1. Wait, what? 6 plus.
You have 6
like,
valence electrons. What would its charge be?
6 valence electrons. So 6 outermost electrons.
Uh-huh. What would its charge be?
It would be 0.
No.
Because isn't it, if it has 6, isn't it, like if it was P6, is that what it's asking?
No.
Would it be
Element
plus
has-
2?
It would
I'm
have...
very confused.
Sean, look on your periodic table and tell me an element that has 6 valence electrons.
Okay.
Oh, it would be 2 minus.
It would be 2 minus. 6
I was
valence
looking at the
electrons.
wrong side of my periodic table. One of them talks about other stuff, and the other, okay, yeah.
Dang, I was saying that the whole time, but I was muted.
No. So sorry. Yeah, so 6 valence electrons, that's group 16. And everything in group 16 with 6 valence electrons has a -2 charge because they need 2 more electrons to get their 8. So if I have a +3 and a -2, if I'm making an ionic compound, those cross. So that's why it's the T2S3. They are sometimes, this is more of an older style question where they used to basically like make up the existence of elements with, you know, like call it T or S or X or something like that, and have you predict what its behavior would be. So I can't imagine that this is something that they would be able to ask a question like this in our new abbreviated test format. All right, what else? Come on, computer. Here we go. So I was like, what? Okay, we're gonna do this one really fast and then call it for a day. So this topic has been on the test for a very long time, and nobody can really remember any question that's actually ever been asked on it. So we'll cover this really fast. But basically, metallic bonding gives us what we think of as that sea of electrons and the behavior of metals. So metallic bonds, again, you've got the cation kind of core of a metal, and it's surrounded by a sea of electrons. Nobody owns the electrons in a metallic solid. This is why they can do things like conduct electricity. It's why you can stretch them out. It's why you can bang them out. It's why you can do all of these things with metals. It's because of the sea of electrons. So I know we very, very briefly discussed that that is basically what a metallic bond looks like. It is super easy to imagine conducting electricity when you've got electrons like this, because the electrons are already everywhere. So it's real easy for them to go somewhere, which is all conducting electricity is, when nobody owns them anyway. It's this alloy part that AP has never seemed to ask about. Alloys are simply mixed metals. Yes. Who had a question? No? Okay. So somebody needs to mute because I'm echoing and it's weird. So alloys are mixtures of metals. That's literally it. But there's two ways to mix them. You can mix them where they're fairly equal, or you can mix them where they're not equal. But a lot of things that you actually think of as metal are alloys. Brass, bronze, steel. Those are all alloys. They're not pure metals. But our main categories of alloys, and this is the part that they've never really asked too much about, is when you have something called an interstitial, inter referring to between. So it's when you have a different metal mixing in between other ones, as opposed to something called a substitution, meaning that they are just taking the place of. The difference here is size. So weirdly, steel is an alloy involving carbon, which you don't think of as a metal, but the little bits of carbon fit in between the iron atoms and make it very, very much stronger, as opposed to brass or bronze, where you have elements that are almost the exact same size that kind of mix together. And if you think about it, brass and bronze are actually much softer alloys than steel is kind of the way to think about it. This is most helpful in pictures. So this picture right here is literally the only thing that you at all remotely should be aware of for this entire topic. So here on the right is what I'm talking about, where it fits in, right? These, like, if you imagined these little purple circles as carbon and the green circles as iron, that's what stainless steel looks like. And since they fit in like this, you can imagine that this interstitial alloy on the right is very rigid, because there's no good space for movement. Everything is filling up the space. As opposed to, say, this bronze on the left, where you've got atoms that are almost the exact same size. And so there's still some very large gaps in here. And therefore, if you hit this thing on the left with a hammer, you can see how there is space for it to move, and it tends to be softer. That's kind of all it is we're talking about. Come on. There we go. All right, literally they talk about just steel and bronze or brass over and over again. Yeah. So like that's it. There's your there's your practice problem. Like this is not a thing they ask about. Really, I don't think it's a thing that they're going to start asking about now, and we've got a really shortened test. So I am not worried about it. Now, this is a question I actually think is kind of interesting, that they could, in theory, tie into a periodic trends, because talking about size could be a periodic trend. So it says gold can be alloyed with many metals. So gold with a radius of 144 and silver with a radius of 144 can be alloyed to form white gold. So which of the following metals would be best to make a substitutional alloy with gold? Substitutional implies that they should be about the same size. So, come on. Computer says I tired. There we go. All right. So out of all of those, the closest one to the size of gold would be the zinc. And that's why you could alloy gold with zinc. That's it. All right. So Wednesday, we're going to review Lewis diagrams, Vesper, formal charges, resonance. That's Wednesday.
All right.
Whew. Yeah.
Miss Baskin,
Yes, Sean.
before we go, right?
Yes, Jim.
I'm still kind of confused about that question regarding the valence electrons. And I just need, my periodic table is here in front of me now, so I need you to explain the whole 6 valence electrons and the charge to me.
How do you know how many valence electrons something has?
The group number.
It is the group number. It is based on the group number.
Oh, okay.
So I don't remember off the top of my head. Does the periodic...
Isn't it based off the second, like the second digit?
Yes.
Like if it's like 16, then the valence electron 6 is like that.
Yep.
Whatever.
Okay. Okay, thank you. Because in my head, right, I was thinking, I don't know why, but when you said valence electrons, like I was thinking of like levels, the different levels.
Ah, yeah.
Because it's like that the outermost level is the valence electrons.
Oh, okay.
But I understand 1, 2, 3, 4, 5, 6. And
Right.
then you said because all of those had what is it, 2 plus?
2 minus.
2 minus. I'm sorry, I don't have the tires on here. I usually get it, but I'm a little sleepy right now. And then you said they crossed because of the 2 units the 2 atoms that they were using.
Yes.
Okay, thank you.
If you do not have, I don't remember because I don't have it in front of me. Does the AP periodic table have group numbers on it at the top?
Yes.
It does? Okay. If you don't have charges written on there, go ahead and write them up. Group 1 is +1. Group 2 is +2. Group 13 is +3. We don't normally have anything for group 14. Group 15 is -3. 16 is -2. 17 is -1. And group 18 is 0.
All the transition metals have 2 valence electrons, right?
They can, but remember they can have other things. So other thing to remember, like you should write on silver's box, silver is always +1. Ag is +1.
And zinc is always +2 and cadmium is always +2.
There you go. Everything else in the transition, you'll have to be told.
Wait, say that one
Can you say that
again.
one time?
Yeah.
Ag.
Ag
I can send a
is,
picture to remind you guys.
yeah, Ag is +1,
Mhm.
and then zinc and cadmium are +2. Everything else in the transition, you'll have to be told.
Okay.
Okay.
My 8th grade periodic, not 8th grade, my
Wait,
regular,
wait,
my
one more
honors
thing.
chem periodic table is popping off right now.
Okay, so for the frequently reviewed questions or whatever, FRQs, whatever, right?
Uh-huh.
I couldn't like type on it yesterday, so like am I supposed to print that out? Like I was confused.
So if you're doing the ones on AP Classroom,
Oh no, I was using the Google Doc. So go on AP Classroom to do that.
oh, so the ones on the Google Doc, that's just what we went through in class. So you can either print that out or just do it on paper. That's just for you, for review.
Oh, so which one are you grading
The ones on AP Classroom.
on Blackboard? I mean, College Board.
Yeah.
Okay, cool.
Yep. So.
All right.
Okay. See you Wednesday.
See you later.